holds up for the lecture. Right, resume of last week. We trained on a very simple pattern recognition problem, 4-bit pictures. We ended up, the pictures, if I remember, were that was picture 1, that was picture 2. That was picture 3, and picture 4 was cross, 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 and cross, cross. They were converted to 4-bit binary vectors, and we used the fixed increment training process, and we ended up with a weight vector that would separate the problem. And after training, we ended up with a weight vector, 4 elements, 0, -1, -1, 2. Now, the training was, even for this simple example, quite complex. We had to go through the training set, change the weights. If you have a weight change during an iteration of the training set, you might have introduced errors for the previous patterns. You have to go back for a second iteration and a third iteration, and for real problems, 100th and 1,000th and a 10,000th iteration to try and correct to find a weight vector that will separate the training set. And we had, for that weight vector, this was the positive class and that was the negative class. That's an arbitrary assignment. If it was the other way around, the weight vector would be 0, +1, +1, -2. Having got the training done, it is relatively easy now to do a testing and using this weight vector to classify other patterns. And if I look at candidate patterns, there's 1, there's pattern 2, pattern 3, and pattern 4. It was that pattern. And it is relatively easy. It's a simple calculation now to classify these patterns. We simply get the scalar product of the vector of the pattern, which in this case would be 0, 0, 0, 1, 0, 0, 0, 1, scanning from the top left. And the scalar product of this, which is W dot I. And remember, we can calculate that as the summation I equals 1 to 4, the 4 dimensions of Wi, which is quite simply 0 times 0 plus -1 times 0 plus -1 times 0 plus 2 times 1. For this example is going to be equal to +2, a threshold of 0. This is the positive class pattern, and this particular pattern would be classified as the positive class. And we can go through the same for the other patterns. Some will be negative, and you might find some which give a 0 response, which means they're on the decision surface. So we can use the trained weight vector very easily, but it is getting that weight vector that is the difficult problem. The training takes the time. And some people who have used neural networks in the past, the argument is we put in a lot of effort in training the system. If it takes an hour, a day, or even a week of training on a computer, once you've got that weight vector, it is easy to use. We then looked at the problem of a well-behaved pattern problem in 2 classes. The pattern we've solved can be regarded as 2 classes A and B in 2 dimensions, simpler than the 4-dimensional pattern problem we've looked at. We've actually defined a decision surface the weight vector would be somewhere out there, and that is at right angles, which would give a positive class there and a negative class there. So that is a simple, easy problem that will find a solution. But now, if we have this, and the pattern space here is well-behaved, completely distinct class of patterns A and a completely different class of patterns B, this problem cannot be solved yet, because if I have a weight vector, it's got to go through the origin. If I have a weight vector there, the decision surface would be there. This would be the plus class, and this would be the minus class. And wherever I change W, it is not going to give a surface which has the A's on one side and the B's on the other side. So there's no solution to that particular problem. The solution is use, and the bias is an extra element. For all patterns, let's call that extra element ID plus 1, where D is the dimensionality, is equal to a constant, usually 1. But for the weight vector, WD plus 1 is a real number. And that enables us, first of all, to classify a pattern at the origin. It also means we can draw a decision surface in our pattern space which doesn't have to go through the origin. And to really understand this, if you take a box, your breakfast cereal box at breakfast would do, this is 3 dimensions, 1, dimension 2, and dimension 3. This is your extra dimension where k would be equal to 1, and that is k. Your patterns are on the front surface of the box, A and B. The weight vector can move in 3 dimensions from the weight vector origin, which is 1 dimension more than the pattern dimension origin. This will define a plane, and the plane can be made to cut the front surface at any orientation. So we can solve, and we can also classify the pattern at the origin. So that is the purpose of the bias. Right, now we come on to look at further problems which have fooled a lot of people over the years and led to misleading results. How much training? What size do the training sets have to be? Now, if we were in a classroom at this point last year, I would ask you all to go out, and I would ask a typical male and a typical female to come and sit in the room. So this is going to be the room, and this is going to be the desk number. And this is going to be the row number. Now, if I have 2 patterns, one person, supposing that is male, comes in there, and that person is a female and sits there. Now, if I only had those 2 patterns for training, you can see quite obviously there's a decision surface, which will have the M on one side and the F on the other. The weight vector would be somewhere out there. So I appear to have got a gender detector by using 2 patterns, one excellent example of a male, one excellent example of a female, and it works for the training set. But when we actually use it on real data, because your gender has got nothing to do with the row number and the desk number of where you're sitting, when we actually test it, we are going to have loads of red crosses there, and we're going to have, those can be the males, and we can have loads of black crosses there. And the training pattern, this pattern is, say, that one there, and this pattern would be that one there. The decision surface based on the green circled patterns would be the straight line there. There is my weight vector. It gets the test pattern correct. It gets the test pattern correct there. But we've got here some females who are being classed as male. And here we're getting some males who are being classed as females. It does not work. And it does not work because, well, first of all, the data is nonsense because it's not related to the outcome, i.e. the gender. But also, it means that whatever pattern you're trying to solve, if you don't have enough training patterns, it will not generalize to solve the solution. Now, the question is, how many patterns do we need? And again, this can't be resolved, but a rule of thumb is number of patterns must be greater than 3 times the dimensionality. So in a 4-dimensional problem, then what we really need is 12 training patterns to prove that we are getting a representative set of patterns to train the system. Now, that's an example with just 2 dimensions. Another example, lottery tickets. I would advise you not to buy too many lottery tickets. Maybe there's a case for buying one occasionally, you just might be lucky. But supposing I take 3 winning numbers for the past 3 draws, and I take 3 losing numbers. Those were the tickets I bought because I haven't won the lottery, and so I'm still teaching you. If you took that, remember the input patterns I is going to be a vector of the number of the ticket as the vector. So we might have 7, 14, 21, 6, 3, 18. 6-element vector, a point in 6-dimensional space. 6-dimensional problem, 6 training patterns. You will find a solution. A solution will separate the winning numbers from the losing numbers. Call that the plus class and that the minus class. And don't get excited. You haven't got a winning number detector because we are separating patterns, even if it's noise, and the lottery numbers we hope are noise and don't have any underlying patterns. Because we don't have enough training patterns, we do not converge. We converge to a solution which does not represent the problem we're trying to solve. Now, looking through the literature, especially in the early days, you will find a lot of people made this mistake. They didn't realize the connection between the number of training patterns and the dimensionality. And when I was doing my PhD long time ago, we were looking at classifying chemical mass spectra. Now, essentially, they were taking a molecule. We have a mass intensity on the vertical. And this is mass. And we have a series of spectrum points going up to about 256. Taking the intensity for each increment of the mass, we would get 256 element vectors. Now, there was a team in America looking at this technique, and they were using a McCulloch and Pitts model to try and classify classes of chemicals. They used 100 patterns per class. $200 in total. And 200 patterns in 256 dimensional space, it converged. It gave them good results on the training data. But it is not a solution to the problem. The data can be completely noise at that level, and you will separate the training data into two classes. So beware. And this is a danger for any of you who might start to use neural networks to try and do some useful classification. If you try a simple example, a few training patterns, two classes, you will most probably get very excited because it appears to classify the training data. Now, it could be you're lucky and we have a situation like that, A and B. If I just took two training patterns there, those two, I would find a solution. And if I keep taking more and more training patterns, the weight vector would not change. So one pattern here or a few patterns will solve that problem. But if we have a situation that looks like this, let's go for reds. And another distribution like this. Again, trying to find a weight vector that will separate the reds from the blues. Can't do it. Each time you iterate through the training data, there will be a change in the weight vector. The weight vector will move around and it will not converge to a solution. So we can converge if we have few training patterns, but it is not solving the problem. Right, so that is an issue with the number of training patterns. The other problem with the network is one we've seen with the distance classifier, and this is linear inseparability. We saw this with the distance classifier. If I have a problem that looks like this, let's draw a set of patterns A, and I have another set of patterns B, which are like that. Now, if these patterns, vector points there, they're perfectly distinct. There's no overlap. But if I try to put a linear surface, then clearly there isn't a straight line that has the red on one side or the black on the other side. So if I specify a weight vector, and if that weight vector is to solve this problem, we cannot have a straight line. We have got to define a curved line. So if the weight vector produces a decision surface that goes round there, and out there, it will solve the problem. How do we get a curved surface? Any suggestions? Looking at the messages, no suggestions. Right, well, the linear surface we are calculating the summation of Wi. These are single terms. It's a first order function. So for a curved surface, need higher order terms. So if a linear system is a first order, go for second order. And this is often referred to as a quadric machine. Now, first of all, let's look at the exhaustive second order. It's a bit like a quadratic equation. Supposing I start off with a vector I equals I1, I2, I3, and I4. Now, with a first order machine, so far, we would find a weight for I1, a weight for I2, and so on. Now, in the second order machine, we expand the vector to give, let's call it I prime. First of all, include all the first order terms. So we will have I1, I2, I3, and I4. That is the weighting of the individual elements. That's what we were doing up till now. We now also include the second order terms. And that is going to be I1 times I2. No, sorry, before we get there. I1 squared, I2 squared, I3 squared, and I4 squared. So we've got now 4 more terms now, which are the squares of the input elements. Now we include the pairs of terms, which will be I1, I2, I1, I3, I1, I4, I2, I3, I2, I4, and finally I3, I4. So what we have is the first order terms. We have the square of the terms, which are the second order terms, and then we have the pairs of inputs. Now note that we don't include I1, I1 because that would be the same as I1 squared. Now mathematically, what we are doing, so in general, the calculation is you calculate the summation I equals 1 to D of Wi, II, the first order terms, plus another summation. Let's change the index to J equals 1 to D of Wj ij squared. That will be the terms. And then for the pairs of terms, we have the summation. And I'll use 2 more constants now. Let's have K equals 1 to L minus 1. Summation of L equals K plus 1 to L of WKL IKIL. Now, if that confuses you, just go back to the original vector and work out the terms, the squares of the terms, and all possible pairs. Now, for a 4-element vector, the second order, the exhaustive second order, be dimensionally much larger. So 4 elements, first order. The second order term is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 elements in the second order. And we've already seen that the training for the system to be robust, the number of training patterns has to be greater, at least than the dimensionality we're using. So this exhaustive transform has expanded the dimensionality and the training becomes harder. This is impractical. Because of dimensionality increase. So it's a good idea, but it's not going to work. What is practical? And this is a strategy called a Phi machine. And the Phi machine is usually written as the Greek letter phi. And this is a nonlinear transform. But not exhaustive. So we don't get the huge expanse in dimensionality. So the strategy is, it's got to be nonlinear. If it was just a linear transform, we would simply zoom in and zoom out on the sets in the pattern space. They wouldn't change position and they would be linearly separable whether they're shrunk or whether they're expanded. So the nonlinear terms are the ones that get rid of the linear inseparability. So the scheme, oh, I spelled that wrong. There should be a C in there. Right. We have a nonlinear transform. We have the original pattern, and let's take 4 dimensions, I1 down to I4. This is your input vector I. Now, the linear transform is something that you choose, and it's trial and error. Try a few nonlinear terms out of the list. Oops, lost it. Of these 14 terms here, choose a few of them. Now, this may seem like a very ad hoc method, but remember the weight vectors we're looking for. There are millions of weight vectors that will solve a given problem. It's not a unique solution that we're finding. Again, think of human beings. None of us think exactly the same way, although we can still do the same tasks. So the nonlinear transform, let's take 4 operations. Let's call this Y1 down to Y4. And this becomes your transformed input. Let's call that the Y vector. And having got the Y vector, one is hoping that we are removing the nonlinearity, the linear inseparability. So the problem at this point becomes linearly separable. And if that is the case, we can use a McCulloch-Pitts neuron with a weight vector to solve the problem. Summation and threshold. So there is a scheme, and the beauty of this is we needn't have an expansion in dimensionality. As long as we've got some nonlinearity, try it and see if it works. Right. Now, a classic problem that doesn't work with a single neuron is the XOR problem. Now, the XOR problem, it can either be a binary problem, and if I look at the patterns on a graph of the XOR function variables a and b, they can be 0 and 1, 0 and 1, f equals a exclusive or b. Now, if I take 0, 0, it is going to be an f equals 0. If I take 1, 1, it is going to be f equals 0. I hope you remember this from level 1. If I take 1, 0, it is going to be f equals 1. And I take 0, 1, f is going to be equal to 1. F equals 0, f equals 1. No linear surface exists. That might be a specific binary XOR problem, but analog XOR does exist, at least it does in pattern recognition. An analog XOR might be a pattern distribution like this. Dimension 1, dimension 2. And supposing I have a cluster over here and a cluster down there. And supposing I have another class which has a cluster there and a cluster there. And to give you an example of where this might occur, supposing we're trying to do character recognition, this could be a cluster of capital A's. This could be a cluster of lowercase a's. This could be a cluster of capital B's. And this could be a cluster of lowercase b's. So where a class has two distinct subsets, we could get an exclusive OR arrangement. Right. Now this problem puzzled researchers in the 1990s, again quite a long time ago, and there was a couple of Americans called Minsky and Papert. And they argued that neural networks didn't have a future because they cannot solve the XOR problem, and this is a real problem in life. Had they have been to my level 1 lectures that you received 2 years ago, you would have realized there is a solution to this, which they actually did stumble across it. Now, how do we solve the XOR problem? Oh, and incidentally, Minsky and Papert, they invented their own name for this neuron model, and they called it a perceptron. Which has gone into the literature as the thing to name these devices. So if you see the word perceptron, it is a McCulloch-Pitts neuron. Right, solve it with a Phi machine. Right. We need a transform. It's got to be non-linear, and it is the trial and error transform that was in the Phi machine. And the transform I'm going to give you from the inputs A and B. I want the hidden transform, the output of here. For the XOR, we've only got two inputs, A and B. I want my Y1 to Y4s, and I'm going to define them as Y1 equals A, Y2 equals B. Because we are using binary variables 0 and 1, arithmetic is difficult because squaring and multiplying, we still get noughts and ones. So I'm going to define Y3, because I know it will work, as a nonlinear modulus, A minus B mod. And because we will have patterns at the origin with XOR, let's have a bias. Y4 is a bias. And that can be equal to 1. So the data we have, A and B are the inputs, 0, 0, 0, 1, 1, 0, and 1, 1. It looks very much like a truth table, or the inputs on the truth table. You should be familiar with that. Let's add the bias. And the bias is going to be a constant 1 for all the input patterns. And if I now add my desired output F, it is going to be for the XOR 0, 1, 1, and 0. Now apply the transform. And the transform is going to be Y1, Y2, Y3, and Y4. And we've got the transforms above. A and B go over for Y1 and Y2, so this is going to be 0, 0, 0, 1, 1, 0, and 1, 1. Y3 is the mod of AB. So 0 minus 0, the mod is going to be 0. 0 minus 1 is minus 1, the mod is 1. 1 minus 0 is 1, the mod is 1. 1 minus 0 is 0, the mod is 0. And Y4 is the bias. So instead of trying to classify this data, we're now going to try and classify the transformed data. And we need a weight vector. You could apply a training algorithm to this, the fixed increment. It would take time, but you should be able to look at the data because it is a simple problem and try and decide a weight vector which will solve the problem. We need to assign a class to the data. So let's have the outputs that are 0 as being negative, and the ones that are positive, 1 are positive. So that is the decision coming from the net to implement the XOR. Right, what weight vector would solve this? Right, having a look at my Y patterns. This has got to be a negative class. 3 elements are 0 and the bias is 1. It means that we must have a negative weight W4. Otherwise, we won't get this first pattern giving a negative response. Let's choose one. Let's say -4. It's negative, it will do. And originally, all the other weights now will still be 0. Let's now go down to the second pattern. This has got to give a positive response. I'm going to get a negative response from Y4 times W4, -1. This has got to be positive. Let's make W3 plus 5. So we've got plus 5 minus 4, 0, 0. Right. Next pattern has to be positive. It is going to be minus 4 times 1 is minus 4, plus 1 times plus 5, minus 4 plus 5 is plus 1, 0 times 1, positive. It's correct. Final pattern, minus 4 plus 0 plus 0 plus 0, negative. Correct. Solution. So the transform, we have solved this linearly inseparable problem. And this is one of many solutions. Now, another solution, can I think of one offhand? Oh, we could have minus 50 plus 61 plus 7 plus 4. And again, I think I'm correct in saying if you use the scalar product of that weight vector with the training data, it will classify and solve the problem. So many solutions possible. Okay, that's fine. I understand and you understand the XOR problem. We are using a certain amount of intelligence to get that nonlinear term. The Phi machine, in principle, come on, move. Oh, you haven't locked up, have you? No. The Phi machine is relying on trial and error. Not very satisfactory, not very scientific. So what Minsky and Papert came up with was, instead of we, the users, choosing by trial and error a transform, why don't we use neurons within this transform box to learn a transform that will solve the problem? And this leads to the concept of the multi-layer perceptron. And I'll try and show you that a multi-layer perceptron can learn a transform. The structure I'm going to use, I'm going to have my two inputs A and B. Now I'm going to draw square boxes which are complete neuron models. A becomes an input there. This is neuron 1. This is neuron 2. This is neuron 3. So in here we've got a weight vector, we've got a summer, and we've got a threshold. A, B is connected to the second one. The outputs go into a third neuron, and we have the final output of the system. Right. Let's call this decision D1 and this D2. Let's have a look at neuron 1. Oh, go away. A and B. 0, 1, 0, 1. F equals 1, F equals 1, F equals 0, F equals 0. Those are the points. And it is linearly inseparable. Let's do the best we can for D1. And let's put D1 in here. D1. It assumes we've got bias going internally in that neuron 1. And let's define this as the positive class and the negative class. If f equals 1 is positive, that would be correct. If f naught is negative, that would be correct. This is correct, but this one is in error, and we cannot do better than having one error in that partition. Let's now look at neuron 2. And again, we'll do the same two-dimensional diagram, A and B. F equals 1, F equals 1, F equals 0, and F equals 0. And let's put in another decision surface. And let's have D2. And let's define D2 as this side negative and this side positive. Checking for errors, F equals 0, negative, correct, correct. F equals 1 on the wrong side, that is incorrect, but this one is correct. But what we've now got is a transform here. The input pattern A and B become outputs D1 and D2. Now there's going to be a threshold, so they could be regarded as 0 or 1, but let's just plot them out as plus and minus. Let's now plot out D1 and D2. Negative, positive, negative, and positive. And let's see where the patterns go. This F equals 1 term. It is on the positive side of D1, and it is on, so the second one, it is on the negative side of D2. So the transform into D1, D2, the hidden space, becomes plus minus. And so we have F equals 1 point there, plus minus. Now the second pattern and the third, because they will have the same, these are the F equals 0 terms. They are D1 is minus and D2 is minus. So what we're going to get is 2 F equals 0 terms at minus minus. And the final pattern is 0, 1. It is on the negative side of D1. It is on the positive side of D2. So it is going to be D1 minus D2 plus. We are going to get F1, change color. F equals 1. So that is our distribution now in the hidden layer space. F1 there, F1 there, and the two F naughts come together. We've done a nonlinear transform, and there they are. And wow! Oh, come back. Don't go and lose. Neuron 3. It is operating on D1, D2. It can perform a linear decision surface. So here is D1, D2 space. A surface that will separate them is a decision surface that goes with the F equals 1 on the plus side and the F equals 0 on the minus side. We have solved the problem. Right. So the system has learnt the transform. And let's just try and have a look at weight vectors for neuron 1. The inputs are going to be A, B, and bias. It is going to be 0, 0, 1, 0, 1, 0. Oh, whoops, 1, sorry. Whoops, bias is always 1. 1, 0, 1, and 1, 1, 1. And the decisions we want is I've lost it now. Going back. Come back. Come back. Oh, don't lose, don't go. It would have to die on me on the last few minutes, wouldn't it? I've lost my... Right, I'm run out of time, folks. I'll have to leave it there. I've lost my whiteboard for the moment. We've got the decision surfaces to solve the problem. I'll start on the next lecture on choosing the weight vectors to perform those decision surfaces for those 3 neurons. So we'll go back a little bit and pick it up next time. And next time, I'm afraid, is going to be on Thursday of this week, because I'm lecturing instead of Tatiana on Thursday. So we'll see you then. Over and out. Goodbye and have a good day.